Yo, what's up, guys? Hang on 1 second. Yo, what is up, guys? Welcome back. Episode 145 today. We're gonna look at some problems. Don't know how many. Probably for about an hour and 45 or so, but we'll jump straight into it. Check out our problem of the day. Oh, hard problem, man. Do I want to do that? No, don't really feel like it. We will take a look. Kind of want to keep going through some of the top 100 like problems again. Let's see, what do we want to take a look at here? Let's take a look at symmetric tree. Start off with a easy. Check whether it is a mirror of itself. Okay. So what are we doing here? Remember looking at this one a little while ago, March 18th. Solved it once. Given the root of a binary tree, check whether it's a mirror of itself, i.e. symmetric around its center. What do we know about this problem? So we go right, left. So symmetric is if like you're kind of looking at it in a mirror, I think. Okay, so I feel like we're going to need to create some sort of helper function. We'll just call it DFS, pass in our root. Let's call that DFS function with our root node. Put a, let's just make this node. If I guess if not node, we can just return. But really, if we want to check symmetric. Symmetric. Is that how you spell symmetric then? I don't even know. Symmetric. Yeah, I think that's how I did it. Yeah. Symmetric. Okay. How we want to check if it's symmetric? Well, let's check. 101. Really, we want to check. Okay. We want to check on node dot left, I think. Node dot left. We need to somehow return false. So maybe we have to keep track of 2 different nodes. So maybe as we go and we check the nodes, we can go, well, let's think about our base cases, right? So if we were to do, okay, well, I think we're going to need, well, I guess the top node is always going to be the same, right? So let's think about this. If we were to pop out our drawing here, we were to go down this tree. Let's take a look at this tree. We go here, here, here. Oh, these are such bad nodes, dude. Oh my gosh. 1. We have a 2 here. We got a 2 here. Right. And then we got our 3. Oh, not a 3. Our 4. Our 3. Then our 3 over here. And our 4 here. Alright, we're looking at this here and we're like, okay. Really, we don't really need to start with this node, right? Because this node is always going to be the same, right? Because there's only one of it, right? So really what we want to do is we want to start at this node in the tree, right? So if we start specifically, we start at node.left, right? This is node.left. I guess we'll just do n.left, right? This is our n.right. Really, our base cases are going to be, well, if there's a node here and there's not a node here, right? I mean, they're obviously not symmetric, so we would probably return false, right? So we do, let's call this node 1, node 2. So if not node 1 or not node 2, we would return false. If not node 1 and not node 2, if not node 1 and not node 2, we would simply return true here, right? Right, and the reason is because, well, if we're looking down here, right, because we're not really checking if they're null. We're looking at these nodes down here. Let's say if they are, right? These nodes are null here, right? So if they're not null, then we can obviously return true, right? We know, obviously, that's our base case. We know that it's true, right? So this can be our base case here. And then we have our symmetric, right, which is where we probably want to return here and where we want to call our function. Want to return trying to think here. I feel like this is where we need to think about the end. Oh man, what is it called, dude? And what? And truth table? What is it? I'm trying to think of a word, dude, but I can't even remember what it is. Alright, so for it to be true, everything needs to be true, right? So we could do, okay, well, return T1 is equal to T2. I don't know, we'd call it N. Whoops. N1 is equal to N2. Okay. And DFS and 1 dot left and 2 dot right and DFS and 1 dot right and 2 dot left, right? Because we would obviously just return our DFS, right? The reason why we use the double and here is because we use the double and because we look at our truth table and we're like, okay, well, 2 1s always going to be a 1. So if something is incorrect here out of these 3, if one of these is false, we're going to return false, right? And then we're just going to keep returning false every single time, really, till we get to the end, right? So every single time it needs to be true, and then we're going to return true. So, and I think this should be right. It should be, if we start with our dot left, we probably want to go dot right here. Root dot right instead of that. Man, my wrist is kind of messed up. Root dot left. So I think we go here, we go n dot left. And then we go n2 dot right. Yeah, they should be the same, but then we go n1 dot right and 2 dot left. So I think this should run. Let's see. So we get a false, but we're not getting true on here, and it should return true. Why are we not getting that? It's because we got a 2 here. Well, that is obviously a typo. Whoops. Let's take a look with, let's take a run on that. Okay, we're still getting false. Why are we getting false here? First and 1 and 2, if not and 2. If not n1 or not n2, turn false. All the best. Appreciate that, Steve Oasis, dude. Thank you for the support, bro. Appreciate that. Why is this not working? If not n1, not n2, return true, return false, we return. I guess maybe we need an if here. No. Right? Return DFS root. I'm honestly not sure why this is not. Turn n1 is equal to n. Maybe it's n2 dot val. That could be it. Nope. N1 dot val. I don't know, dude. Does anyone have any ideas? I'm honestly not sure. I don't know why this is passing. It seems right to me. We got a not here. Didn't see that. What a typo right there. There we go. Something stupid. So didn't even notice that. Just had a not. Was messing it up. There we go. Cool. Let's jump into another problem. Kind of just gone through some old problems. I feel like it's important to revisit problems that you've done before. Just make sure like the intuition is still there. We're going to be doing a bunch of just binary tree problems. Maybe we take a look at this. Binary tree, right side view. Given a root of a binary tree, imagine yourself standing on the right side of it. Return the values of nodes you can see ordered from top to bottom. Okay. So instantly my thought here is to apply BFS right here. Of course, people that are probably returning that maybe have watched me do this before, BFS is my favorite thing to do. Right? So when we think about BFS, we think about this right here, right? We got our 2 here. We got our 3 here. We got our 4 down here. Whoops. We got our 5 here, right? Really what we want to return here is we want to return our values on the right side of our tree here, right? So we're looking at this one, and this one, right? Let me switch colors here. So I think when we apply BFS, like we know what like the basic of BFS is, right? When we think about DFS, we're taking one path and going all the way through, you know, whatever path that is, you know, we can take this one or, you know, whatever, right? But in BFS, we're doing like level traversal, right? So really what we can do is that we can do just simple like iterative BFS using a queue. We can start at our first value, right? Then check if this is the last value in the this is the last value in the level, right? And we can reference that using like the end of a for loop, right? We can check the length of the queue and reference it length of the queue -1. And then as soon as we hit that, we know, well, this is the last element, right? And this is the last element, right? And we would simply just add these two, looks like an array here, right? So here we're doing 1, 3, 4, 5. But here we also have a 5 here. So wait, no. Wait, is this part of... Okay. I thought this was part of this one. So it looks like here that we've got our own over here, right? So really what we want to do here is we want to do BFS, right? The way we do that is we want to initialize our queue, right? Okay, probably import our modules. So from collections, import the queue. Come down here. Start off with our while queue, right? We probably want to pass in our first value, right? And our first value is going to be queue.append. Want to pass in the root, right? So in this case, yeah, probably just root.val, right? So here, we don't really need to keep track of our index here, so we can loop through the length of our queue, right? We can take the length of our queue here, right? So make it a little more, looks better, you know? Take the length of our queue here, take the range of our length, and then what we can do here is we can pop, right? Because we know what the length of our queue is, right? And we can do an if statement here. Instead of here, sorry, we do the if statement here and we check, okay, well, we can check, okay, if the length, if, maybe here we would need the index. So let's do for I in range length, right? So we check, okay, well, if I is equal to the length -1, right? Which references our last element in our length of our queue, right? Because we're, yeah, I think you guys will see at the end. Then we would simply add this, right? Res.append, we would append our I, right? Let's initialize a res array, something that we're going to return, okay? And then we simply down here, inside the for loop, I think we probably want to add our, add our stuff. Would we add it inside the for loop? Honestly, I can't really remember. Trying to think. For inside of our for loop here, we're iterating by level. You do q.pop left. So let's say we're here, right? We popped here. Right, because we're taking the length here outside of the for loop. So I think we're fine. So I think we should do it inside of our for loop here. So I think we would go, okay, well, if no dot left, just do q.append no dot left. If no dot right, do q.append no dot right. And then we would simply just return our res. So I believe this should work. Node. We're not even popping it. Let's do node is equal to q.left. Pop left. So I think that should work now. has no attribute left. If node dot left, int object has no attribute left. Q dot append node dot left. If node dot right. Why are we in this error here? Has no attribute left into object. Oh, it's because we're appending root.val. We want to just append the actual node. Nope. Why is that? Object has no attribute left. Maybe it's the if root if not root, we'll return an empty string. Maybe it could be this. It could be our empty string base case here. Okay, there you go. That's what it was. Okay, so we're returning the empty string here, but we're getting something incorrect here. We're getting 0, 1, 1. Res.append I. We want to append node.val. We're appending our I, what we're at. Put an if statement before pop left. Sorry, Kabir. You said put an if statement before pop left. Why would we put the if statement before pop left? We haven't even popped the node, so that probably wouldn't really work there. If you're only always getting the right node, then this is like iterating over a linked list. Yeah, I got that right there. Oh, after, my bad. Yeah, I got it. I got the if statement after here. Seems like you got it working. Yeah, I think we got it working. If you're only always getting the right node, then this is like iterating over a linked list. No, not really. It's not really like iterating over a linked list. We're performing BFS here, so we're looking for the rightmost node. And the reason why BFS works here is because we can traverse by level, right? So, we start off here, we're traversing by level, and that's how we're using the for loop here, right? So we use the for loop, and we get the length of our queue, right? And that's the reason why we know how many iterations to do on the for loop. So we'd be iterating it, and then we use this if statement here. We do if I is equal to the length of -1, which references the last element right here every single time, right? And then we add it every time, at every single level. So appreciate that, Kabir. Carry on, good job. So let's see if this submits. There we go. Yay. Sweet. Take a look at another problem. Kate, smallest element in BST. Let's take a look at lowest common ancestor. 236, lowest common ancestor of a binary tree. Given a binary tree, find the lowest common ancestor LCA of two given nodes in the tree. The lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants. The lowest common ancestor is defined between nodes P and Q. P and Q. So what are we given here? So we're given P. We're given Q. 5 and 1. So these are the two nodes that we're looking at here. And we want to find the lowest common ancestor of nodes 5 and 1 is 3. The lowest common ancestor. Why is it 3? Is this 3 here? According to the definition, the lowest common in graph theory in computer science, the lowest common ancestor is also the least common ancestor of two nodes in a tree. Okay, we can define each node to be the descendant of itself. Okay, let's take a look at another example. So here we got 5 and 4. So is P and Q always unique? P does not equal Q. P and Q will exist in the tree. Okay, so I believe that means it's probably unique. Why are you still here just to suffer? Oh, jeez, I'm going to sneeze in a second. Oh my gosh, dude. Bless me. Why am I here? Just to suffer? I mean, not really. To be honest, bro, I actually kind of enjoy doing it. I don't know. I've been doing it for like 5 months, so it's kind of just like part of my routine. I just do a couple problems a day. So I don't know. It's alright. It's pretty fun. I enjoy it. So I'm not really good at it at all, but I feel like I'm fairly average. But it's fun. Just like, I don't know, problem solving for a bit. I don't know. Let's take a look here. Think about this. P is equal 5. So here the LCA of nodes 5 and 4 is 5. 5 and 4 is 5. That's because we don't have another number in the opposite tree, since a node can be a descendant of itself according to the LCA definition. I remember looking at this problem, man, but it's been a little while. I think I remember it being fairly tough, like, because there's so many different, I feel like, cases to think about. So here we got 3. So I feel like the way to kind of go about this, maybe we can pull this up. Like this tree's fairly big, so I feel like it's kind of hard to. We get 3 here. We get 5. Do 1. Okay, we go 6 here. We go 2. We go 7. It's terrible 7, man. 7, 4, 1, 0, 8. So really, I'm gonna circle the. So these. Oh my gosh, didn't switch color, dude. What's going on here? So we start off here. We start off here. Right, so these are the nodes that we're looking for, right? So I feel like somehow, you know, obviously we got to start at this node, right? So we start off our function at this node. We traverse. Is it possible to create music by using programming languages or code? I don't know, bro. I don't think so, but I don't know. I don't know. To be honest, I don't really know. So maybe search it up on Google, dude. I don't know. Yeah, so I feel like we gotta have some sort of flag to know that we found our P, we found our Q, but somehow also keep track of our parent, right? Because web audio API, for example. Yeah, check that out. I've got no idea, man. Got no idea about that stuff. To be honest, I don't really know if I understand your question, how to create music by using programming languages. I don't know. Maybe check out that API, like what marching person said. So anyway, yeah, we got to have some sort of flag here. We got to keep track of our parent, I feel like, right? Because if our parent here is not, let's say maybe our node that we were looking for was, 4 or something, right? If we can't find our P or our Q in one side of the tree, then I feel like we would instantly know that our lowest common ancestor would be itself, right? If we don't, and I think that's the right way to think about it. I don't know if someone in here maybe knows how to solve this problem, but I think that's probably the right way to think about this problem. Is that pretty much we got to kind of search this tree, find our P and our Q. If they're in one tree, then really it's our node that is from here. If not, if we find them in 2 separate trees, the lowest common ancestor would be the parent of the highest node in the tree. But to think about that and to put that into steps of code, I feel like is kind of tough. Tough to think about. Anyone else like got some ideas or something? I don't know. So I guess first of all we can think about our base case functions, right? So we have our DFS here. Probably want to pass in our root, right? Start with that. Actually, I want to learn programming language. I want to learn programming, but I think what if programmers are going to be replaced by AI? Can it be true? Yeah, bro. I mean, yeah, it's probably true. Yeah, it probably can be replaced, but I feel like it's the same with everything, bro. Like you can think of any job probably that can be probably replaced, but I don't know, man. Just do what you want to do, bro. If you want to learn, just learn, dude. I don't think you really need to worry about that. Just if you like doing it, you like doing it. So I feel like that's all that matters, bro. It's a passion that counts, man. Okay. Think about our base case, right? So really, our base case here would probably be, well, if it's our root, if it's the root node, right? If one of our, really, if we think about this here, I'm going to keep switching colors because I don't want to keep removing all this, but if we think about it, I think our root would be the base case, right? So if our, because really if you think about it, if our lowest common ancestor, if one of our P or our Q is root, right, then really the highest lowest common ancestor can only be the root. So I think, one of our base cases would be, well, if I'm trying to think here. What are we returning? We're returning tree nodes. Okay, so if P or Q, if, how would we do this? Would that be the base case though? I don't know. That wouldn't work though, because how would we keep track of what node we visited? So maybe we would do, okay, well, if node is equal to P, so if root is none, or if not root, or root is equal to P, or root is equal to Q. Maybe get rid of that. If root is equal to P, or root is equal to Q. I guess that meant to be node, not root, but we would return our node. If root is equal to P, if node is equal to P, node is equal to Q. Well, since we're searching through this list, right, I feel like it's fairly obvious that we got to call our recursive function again. So if we're only passing one variable, but here's the thing, maybe we have two separate nodes because, I don't know. I'm kind of stuck, not gonna lie. Let's take a look at the internet. There's a 6-minute video on Necode. Seems kind of tempting. Is there like a written explanation? That was common ancestor in binary tree. Can you use recursion to traverse the array? Can you figure out the conditions we encounter when choosing a path between the left and right subtrees during traversal? Using the values 2 nodes, perhaps you can determine the LCA by traversing based on these conditions. If P and Q are in different subtrees, so we thought about that. That's what we thought about earlier, right? A split occurs, making the current node the LCA. If both are in the left or right subtree, the LCA lies in that subtree, and we further choose that subtree to traverse using recursion. Yeah, man, I'm kind of stuck, dude. Jeez. DFS a tree when the node val is different than Q or P. That's the common ancestor. When the val is different than P or Q. That is a common ancestor. I don't think so, Wally. I don't think so. The common ancestor is the common ancestor of the two nodes, right? So, I mean, we look at this graph here, right? We start with P and Q is what we're looking for. So we see P is 5 here, Q is 1 here. The lowest common ancestor would be 3, right? Because they're in separate trees, right? We look for the ancestor that they're both connected to, right? But instead in this graph over here, we see that P is 5 and Q is 4, right? So they're in the same side of the tree. So then the ancestor would be itself. Necode has binary search tree, not a binary tree. For the given problem. I think it's probably the same thing. There's just a different problem. I think that's the same thing, a binary search tree and a binary tree. I think it is, but I don't know. Am I wrong? One and 5 are going in a different direction from 3. Yeah, I know. Yeah, that's why it's the lowest common ancestor, right? Because they're going in a different direction. That's the common ancestor, right? But instead, if they're in the same side of the tree, then the common answer would be itself, right? Because you can't have any other common ancestors between them. Does that make sense? If they are going in the same direction, they keep traversing. Yeah. Maybe we jump in and check a NeetCode video. I mean, he does have a 5-minute video on it, so maybe it'll give us Kraken Fang. Look, NeetCode's got a 6-minute video. Let's take a
How to use AutoQuote Explorer. First, start a quote. Then, compare rates from us and our competitors.
Hey everyone, welcome back, and let's write some more neat code today. So today we're going to solve lowest common ancestor.
Does it, bro? I honestly don't know off the top of my head. I didn't really think about that. Let's take a look. You are right, yeah. Yeah, you are right. But I don't think that really matters though. Low key could be it because it's the same sort of problem. Right, because if you have a binary search tree or you have a binary tree, you know, it really just means that you know, it's in proper format, a binary search tree, but does it really matter? Because we're not really looking at the values necessarily. We're looking for the lowest common ancestor, so it's the same thing either way, right? Let's take a look at the video.
Hey everyone, welcome back, and let's write some more neat code today. So today we're going to solve lowest common ancestor of a binary search tree. And if you recall a while ago in a video, I showed you guys this is basically to be this node in the tree such that P and Q are descendants of this node, or P or Q happens to be equal to this node. So basically, what we're saying is 6 can technically be a descendant of itself. So for example, in this example, we're given P equals 2, Q equals 8. So we're going to start at the root because the root is always going to be a common ancestor of every single node in the tree, right? That's just kind of basic, right? For, you know, this node and this node, of course, this is going to be a common ancestor. It's not necessarily the lowest common ancestor, but it is a common ancestor. So what we're going to see is P is less than 6. Therefore, it's going to be in the left subtree, and it actually happens to be a direct child of 6. 8 happens to be greater than 6.
I think you are right. To think about it a different way could be. I was wrong. I thought it'd be the other way around, but I think you're right because he's talking about it being we're checking if it's less than or greater than. So maybe this is a different problem. I don't know. Let me see how I did it a couple months ago. Cause I don't know how to do it. So okay, so we used if not node, we return none. Our base case, we got that. I mean, we knew that was pretty straightforward, right? If node is equal to P or node is equal to Q, we return node. Recursively check the left, recursively check the right. If left and right, so if we found both, we return left, if left, else right. See, man, it's so simple, man. It's just so tough. Like, the code is so simple to follow. You know, a simple recursive function, but, you know, sometimes, like, when you're I feel like when you're on the spot, it's definitely tough. Like, let's see if we can do it. If not node, we want to return none, right? This will be our base here. If node is equal to P or node is equal to Q, we return node, right? Here we'd pass in our P, pass in our Q. Let's take a look. Go through this. Right, so this is our base case, right? We obviously want to check our left, right? So we would go, okay. Call our DFS function again. Node.left. Our P and our Q. We'll do our right, DFS, node.right. P and Q. And then we check, okay, well, if left and right, which means we have found something, right? We'd return it up the recursion stack. There has to be a more intuitive solution in the solution section. Yeah, I mean, there probably is, but I'll take a look after this one we look at. So what do we do if we found left and right? we want to return the. So if we found our nodes, if left and right, we'd probably want to return our node, right? Because that would be our parent value in this case. Let me check let's check the solution I did a couple months ago. Yeah, if left and right, we return the node, right? Then we have this other base case here. Sorry, not base case, return case, where we return left, if left, else right. If left, else right. Turn left, if left, else right. Why do we have this case here? Return left, if left, else right. What is the reason here? So if we find both, we return our node. If we don't find both, then okay, we would return left if left has a value. And the reason is because I know what this is doing, but I don't understand the why behind this. Like, why would we do this? Like, why, if we only find our left, we're guaranteed to find both, but if we only find our left, then why? Let's call the function. Let's just make sure this is right. Let's call our function DFS. Pass in our root. Thank you. I guess we can probably return, right? Okay, so this is right, but why this here? I'm curious. I'm gonna paste it into AI and ask it why. Why return left, if left, else right? Left is not none, return left. But I thought here is guaranteed that we find something. P and Q will exist in the tree, so. If P or Q in the left or right subtree, send it up. Oh, okay, I understand. Right, so we're just returning this up the tree, right? Because technically we're returning these to the recursion stack, but if we've only found one of them, we keep returning it up. If that's left or right until we found both. Post-order traversal, there's a chance you will find either left or right first, and you need to return that back to the previous call. Yeah, I think that's what I just said. I agree, Kabir. I agree. Let's submit this. We looked at it again. We couldn't get it, but I don't know. That's all right. You always come back to it in a couple months, you know. Let's jump out of binary trees. Let's do something different. I feel like we've been doing binary trees for like an hour now, so. I always like to do a graph problem every day. So let's take a look at a graph problem. Word ladder BFS, no matrix graphs, graph theory, find the town judge. Take a look at an easy problem. In a town, there are n people labeled from 1 to n. There is rumor that one of these people is secretly the town judge. Town judge exists then. The town judge trusts nobody. Everybody, except for the town judge, trusts the town judge. There's exactly one person that's satisfied. there's exactly one person that satisfies properties 1 and 2. You're given an array trust where trust I is equal to AI, BI, representing that the person labeled AI trusts BI. If a trust relationship does not exist in a trust array, then such a trust relationship does not exist. Return the label of the town judge if the town judge exists and can be identified, or return -1 otherwise. So if you find both and you are returning back, then you'll land on the closest ancestor and we'll return that node. Yep. I got that. Sweet, Kabir. Thank you for that, bro. That was definitely a tricky problem, for sure. Okay. So let's take a look at this. Let's go to 50% acceptance rate. Interesting. So pretty much what we're doing here, let's plan out our solution here. I think I have an idea about how you want to do this. So we're given our trust array here, right? And we're given trust where trust I is AI, BI, representing that the person labeled AI trusts the person labeled BI. If a trust relation does not exist in the trust array, then such a trust relation doesn't exist. So we're looking for a town judge. Everybody except for the town judge trusts the town judge. So pretty much. Okay, so what I'm thinking is that the town judge cannot go anywhere, so that shouldn't have any. It shouldn't have any out edges. The town judge, but it should only have incoming edges. But it should have incoming edges from every other node. Does that make sense? I think that's probably the idea here, right? So we have. Let's look at this one, right? So we have 1, 3, right? So really technically we can draw our node here, right? So we have node 1. Node 1 can go to node 3, right? And node 2 can go to node 3. So that's exactly what I said, right? This node has no outgoing edges, right? It only has incoming edges. So let's look at another example, right? Let's look at the one where they -1, right? They can't figure it out, right? So let's look at, we have 1 goes to 3, right? Then we have 2 can go to 3. Oh, whoops, my bad. Let's do it a different way. We got 2 can go to 3. And then we got 3 can go to 1, right? So this has a outgoing edge. So really, I think what we can do is that we can loop through this list. We can make an adjacency list out of this, loop through the adjacency list, and if a node doesn't have an outgoing edge, doesn't have any outgoing edges, then I think that's the one that we want to return. Could that work? I don't know. I guess we shall find out. So let's create an adjacency list here where we pass in our edges. We can create a graph here. We can go, okay, well, for edge in edges, our AB can be edge. And then we do, okay, well, if A not in graph, we do graph A is equal to B, or graph A is equal to this. And if B not in graph B is equal to this. And then we probably want to do graph A dot append B, right? Return our graph. Let's call our function here. Assign it a variable. Right, and print our graph. Cannot access graph. This needs to be trust. They also give us an AND value here. Could that solve the problem though? Just counting the one with the outgoing edges. I don't know. So then if we go, okay, well for key value in graph.items, we can check, okay, well graph let's check, well, if graph key, right, because this should equal to this, we would return key. I don't know. This is definitely probably not going to work. Graph key and a hash pool type list. What is going on here? Graph.items. Oh. Let's just get rid of this. That's for our dot items would be taking both the key and the value, I think. Okay, so it's not just that, right? We also have to, it's not just counting the ones without an outgoing edge. We also have to think about where we're visiting here, right? So maybe we got to do maybe some sort of DFS function that loops through it. But I feel like with an easy problem, you shouldn't be doing a DFS function with this. I feel like that's a little bit overkill. So I feel like there's some sort of trick to it. Trying to think here. If there's an outgoing edge, town judge trusts nobody, everybody except for the town judge trusts the town judge. I'm trying to think here. Anyone got any ideas, you think? Is there any discussion? Together. Okay. First saying, I am from Pakistan, struggling with unemployment. I am a game developer using C# and Uni. I've been unemployed since 2024. Sorry to hear that, bro. I can't even offer you any advice too, bro, because I don't got a job either, so. But I hope the best for you, dude. Just keep grinding. Keep grinding and keep applying, dude. Let's see here. Trying to think. How can we do this DFS function? We loop through, we check. I don't think DFS would work here. I think it's overkill. I can't think of any way like having a DFS function here would probably work. So maybe we can loop through, right? So we have, currently right now we have an adjacency list, right? Okay, we got a graph here. Sorry, this is meant to be something else. It's meant to be a truss here. Right? So I think how we can do it is we can kind of do it the way we would think about it, right? So, right, so we do, for key and graph, we check if our graph key is equal to this, so, right? We loop through, if it is, we add it to res, right? So we would go, oh, sorry, let's just call it res.append key, right? Let's create a little, a res function here, right? I think what we can do here is we can find out which ones are our, cannot assign subscript here, maybe, oh, whoops, need a double equals. Oh, leak code free, man. Leak code free. Okay, right, so we get a 2 here. In this case, we only get 1. In this one, we only get 1. This one, we get none, right? So we go, okay, well, we can then check, right? So for, well, actually, really, why would we need to add it to res? Because I'm sure there's a case where you can probably, yeah, I'm sure we might need to. I don't know. So then we can go for judge in res. Maybe we can get that judge and count how many times it's trusted somehow. So we can go for judge and res, right? We get our judge. And we go for judge and res, we go for judge and res. Do we need another for loop to can we do that from here? Can we go can we loop through the values as well, maybe? Right, so we go for key and graph. Key is this, we loop through. No. Man, I'm trying to think here. Honestly, not sure. I thought I was cooking for a second, but maybe not. For judge and res, maybe we can go for AB in. For AB in what is it called? Trust. Trust if judge is equal to B, right? Because we're looking at an outgoing edge. Then we can do count plus or equal to 1. If we see a if n minus 1 is equal to count, we would return that judge. If nowhere in this loop, we would return -1. Let's see, does this maybe work? I don't know. Can I access local variable count? Oh. Oh, there we go. Let's see if this submits. I don't know. Oh my gosh, dude. 91 out of 92 test cases passed. N is equal to 1. What are we missing here? So if trust is empty, what, we return 1? If trust is, if the length of trust is equal to 1, what, we want to return 1? No, sorry. If, what is this edge case here, dude? Sorry, if trust is equal to this, we return 1. What is this edge case, dude? Like, trust is equal to for what? What are we missing here, dude? This is crazy. This has never happened to me. I don't know. Output 1, but we expect -1. How are we outputting 1? Oh, it's not because of this. Okay. It's because of something down here. Mine looks good. Judge gravy, we count. If not, then we would return -1. This looks good. Keying graph. Build that res array here. Yeah, bro, what is wrong here? I'm getting 91 out of 92 test cases. What is wrong? My bug lies in my adjacency list. Function only adds people to the graph if they appear in trust list, but if someone trusts nobody, they will be missing from a graph. Ah, that's why it's not working. So what we gotta do Okay, we can get rid of this. We can build our nodes first. Build nodes first, and we can go, okay, well, for I in range n, starting from 1 to n, we do graph I is equal to this. For origin AB, key error 3. Let's just leave it to n. We go to n. Still getting a key error. Is it n minus 1? Still getting a key error. Why are we getting this key error, dude? What is this key error? Why are we getting a key error? I don't understand. One small mistake, you initialize a key 0 to n minus. From 1 to n plus 1, dude? What? Why is it 1 to n plus 1? Why do you use Linux? To be honest, man, I really enjoy it. I like it's faster. It's I feel like Windows is just really slow. I still use Windows though. I dual boot my computer, so I have Windows on the other hard drive and I play games on the other hard drive, and I just like Linux because of how fast it is. I like the terminal. I like the initial learning curve for it. I've only switched for like 3 or 4 months, but like the initial learning curve was kind of tough, but once I kind of got comfortable with the terminal, like it was fine. I don't know, I kind of really enjoy it. So I don't know if that really answers your question, but just pretty much because it's faster, there's less bullshit on Linux. You know, it doesn't come with a bunch of pre-installed shit. You know, I can make my computer how I want it to be and have control over it, and yeah, so that's why I like it. Let's see if this submits. Okay, there we go. Let's see, how did I do it last time? A couple months ago I did this. Okay, so we did it kind of the same way. Definitely was an interesting problem, hard to think about, but we got there in the end, so probably do one more problem today. Let's take a look. Let's find a good problem to finish off with. Oh, we did get a new problem of the day. Divide array into arrays with max difference. We'll probably do this tomorrow, because I kind of want to save something for tomorrow. So, okay, I get it. Do you use Linux, Wesley? Have you ever thought about switching, or? Let's take a look. Top 100. Link list cycle. Why don't we take a look at sliding window, dropping rainbow to move zeros, 2 pointers. Dude, I don't know what to pick, man. Tough. Let's do running oranges. It's been a while. No times in grid. Nah, actually, let's not do this. This problem's too easy. I feel like I know how to solve this. So I'm gonna do something that's kind of challenging. I don't know. Anyone got an idea what to do? I don't know, dude. What about letter combinations of a phone number? Dual backtracking problem. Oh well, I guess done this one too recently, so not this one. Let's do a sliding window. I struggled with the sliding window a couple days ago when we tried one of the problems, so maybe we should take a look at this one again. I feel like it's been a while. Yeah, it's been about 4 months since we solved this problem, so probably a good time to look at it again. So we're given two strings S and P, return an array of all the start indices of P, anagrams in S. So we're looking for ABC in S, P's anagrams in S. So the substring with starting index 0 is CVA, which is an anagram of ABC. It's an anagram of ABC. So we probably want to start with our left pointer. Loop through for right in range length. For right in range length S, right? We probably want to do my dictionary is equal to counter of P, right? We count, if we use this, right? And what we want to do is we want to do, okay, well, are we doing is it consistent? Why do we output 0 to 6? We're returning the start index. CBA or BAC? Well, the start indices, so we've got to keep track of our start indices. So we're only keeping track of, I think, stuff that's like... So we got AB here, in this case. Then we got BA, which is another one. And then we get AB. So maybe we're going to have to use maybe some sort of while loop or something. I think. Find all anagrams in a string. I think probably a while loop is probably the right idea here. I feel like we're probably going to need a res array. If I is greater than or equal to P, yeah, honestly, dude, I'm kind of struggling with sliding windows, bro. I gotta get better at these. I gotta start looking at them again. It's been so long. Length P. We use a counter here. What are we doing here? We're taking the counter of S. We're taking everything from the length of P minus 1. I wonder why we're doing this here. Check if it's the same. Shrink window. Length is equal to length P. P count is equal to counter P. S count is equal to counter res. I don't really understand. Why are we going from the length P minus 1? You are practicing programming problems for interviews. Are you interested in doing projects to put on your resume as well? Yeah, I am, dude. I work on my own personal projects and stuff like that. Nothing out of the world or anything, but I do, yeah. And I have stuff on my resume. I've done a few internships as well. So yeah. Definitely tough. Been trying to network on LinkedIn, you know, message recruiters and stuff like that. It's you know, I try hard to use LinkedIn. I don't know if, I mean, if anyone watching this does this too, but we have like a LinkedIn page for the university that I went to, that I graduated from, and like there's an alumni page, and like people that put their university on the LinkedIn are like, I think, on the alumni section. I don't know how it really works, something like that, but you know, try and go through that and try and connect with tech recruiters or connect with engineers, and you know, message them, try and build a connection, you know, try and set up a call or something like that, but has like a 1 out of 10 1 out of 10 probably not even 1 out of 10, bro. I'd probably say 1 out of 30 or something chance of like working, that someone actually responds to the message. No, I think I craft a pretty decent message that's like, you know, I wouldn't say like very, very personalized to something, but I would feel like pretty personalized to them, but it's just like tough to get those replies, I think. But yeah, gotta figure out why this is doing this. P count. So we take the counter. We got S count. Let's analyze this code. Take the left. We take. Why do we take the count at the other one though? I'm curious here. S count is equal to counter S. Why are we slicing from the length of P minus 1? I don't really know. Let's print this. Print P underscore count. Here we're looking at, why are we doing this? Why are we slicing by the length of P minus 1 here? I don't get that. That's the only thing I don't understand. Why we're doing that. think I gotta go do let's see, is there a sliding window leak code list? I gotta revisit my sliding window skills, man. There is. Probably jump through this a little bit, take a look at some of these problems tomorrow or something. Need to refresh myself. S count is initialized with the first characters of S. This sets up a sliding window so we can add one character and check the full window in the loop. Ah, okay. So then we start at where we slice from. We add it. We check if it's the same. It's not. If it is, we add. If not, we shrink on the left side. If S count, S left is equal to 0, then we delete it. Then we increase our left pointer. Okay. It's an interesting way to think about the problem, man. It's just like, it's tough, man. I don't get that intuition. Length P minus 1, length S, right? So we start there, we expand our window, right? Expand. If our S right, plus or equal to 1, right? We check if they're equal, right? So we do if S underscore count is equal to P underscore count, then we want to res.append would be S left? Yeah. Res.append left. Right, we check if they're the same. If they're not, then we would, what would we do from here? We would take a look at our left value. Our far left value. We probably S left. S count left minus or equal to 1. And then we check if it's 0. So if S underscore check 0, if S underscore count S left if you don't mind me asking, what kind of software role are you aiming for? Front end, back end? If I'm gonna be completely honest with you, marching person, it's probably if I had a preference, probably a back end role. I do full stack, so I wouldn't mind either, but I don't know, I feel like I'm more logic based and I kinda like back end stuff more, so probably back end. But I do both, dude. Honestly, I do both, so yeah. Okay, if S count S left is equal to 0, then we want to delete S underscore count S left. And then what we want to do is we want to increase our left by 1. Okay, we forgot the S here, but if S count S left is equal to 0, we delete our S count, we increase, yeah, and then we would just return outside here. Return res. Let's take a look at this. Okay. Definitely gonna get back into the sliding window problems. I used to love sliding window problems too, which is the crazy part about it. I mean, I still do. I don't hate them, but they were my favorite problem to do. So definitely just gotta mess around with it a little bit more. But I think I'm gonna call it there. I appreciate you guys watching today. I'll be back at it same time tomorrow. It's probably around 6:30 Central, 6 p.m. Central. So appreciate you guys watching, and I will see you guys tomorrow, like usual. So